Hi, my name is John Crockmalney, and I've developed these visual tutorials to accompany any technical training format that might be delivered. In this presentation, we'll explore simple electrical circuits. In this presentation, there will be three learning outcomes. Number one, describe simple electrical circuits. Number two, apply Ohm's law to simple electrical circuits. And number three, measure for those simple electrical circuit terms. We might remember that there are three components of any electrical circuit: a source of the power, the load, and the conductors. An electrical ladder diagram is shown featuring these components. What provides energy to the electrical circuit is the power source. In this graphic, we see 120 volts AC power applied to terminals L1 and neutral, shown as the letter N. The load of the ladder diagram is shown by the symbol representing a red light bulb. Notice the circle representing any load, the diagonal lines coming out from the circle representing a lamp, and the letter R for the color. In this graphic, we see that if measured, this load will register 120 ohms of resistance to the electrical current. Conductors are what connects the load to the source of the electrical power. These are the wires of the circuit, but could also be termination blocks, wire nuts, and wire connections. It is understood that simple electrical circuits only have one load. This load is connected to the power source by the conductors. A load converts one form of energy to another, in this case, the electrical energy into heat and light of the light bulb. This graphic shows a ladder diagram and the applied voltage of 120 volts AC power being connected to a 120 ohm light bulb. Above the light bulb symbol, you'll notice an LT-1. The LT-1 identifies this one load offering resistance in the circuit. With 120 volts powering the circuit and 120 ohms of resistance, we calculate 1.0 amps flowing through the circuit. This slide shows a ladder diagram showing the applied voltage being 24 volts AC power being connected to a 120 ohm light bulb. Above the light bulb symbol, you'll notice an LT-1. With 120 volts flowing in this circuit, we identify 0.2 amps flowing. Remembering Ohm's law, we can understand the relationship among pressure, flow, and the resistance to that flow. In this fluid power circuit, between terminals L1 and N, we see a pressure difference of 120 psi. Between terminals 4 and 5, we see the circuit load. The circuit load will convert the pressure and flow of the circuit into rotational mechanical torque. If your hand were inserted into the L1 position, it would deflect away from the pump located immediately upstream from it. This is due to the discharge pressure being produced by the pump. I'll place a positive above the L1 terminal, signifying this positive pressure. If your hand were inserted into the N position, it would deflect toward the pump due to the suction pressure of the pump. This is the pressure difference made possible by the pump. I'll place a negative above the N terminal, signifying this negative pressure. Terminals L1, 1, 3, and 4 are in the red because they are under the pump's discharge pressure. If your hand were placed into these positions, it would deflect away from the pump. Notice the positive symbols next to the terminals. Terminals N, 2, 7, 6, and 5 are in blue due to the suction pressure developed by the pump. If your hand were placed into these areas, your hand would deflect towards the pump. Again, notice the negative symbols. It is this circuit pressure difference that causes the flow of water in the circuit. Remember, the greater the pressure difference, the greater the flow rate that results. The lower the pressure difference, the smaller the flow rate. Focusing on the load itself, we see 120 psi difference across the load. Water flow under 120 psi pressure is presented to the load shown as a paddle wheel and causes rotational mechanical torque. Pressure at terminal 4 is measured at 120 psi, while the pressure at terminal 5 is measured at 0. In this graphic, energy is converted from fluid power into the rotational mechanical torque. In order for any flow to happen, there needs to be a pressure difference. The green dashed line represents the division between the two pressures. 120 psi discharge pressure on the right and 0 psi suction pressure on the left. Any pressure difference will result in a flow if a means of conduction is present. Any flow is measured by having all the measured material passing through the meter. If we are to measure flow in this circuit, notice that the circuit is broken into and the meter is installed. All of the liquid matter flows through the meter for measurement. With a load in the circuit, a flow meter could be placed anywhere in the circuit and the same value would be recorded. If 5 GPM were read between terminals L1 and 1, 5 GPM will be read between terminals 5 and 6, and also between N and 2. This ladder diagram shows that with 120 volts of AC power being applied to a load having 120 ohms, 1 amp flows through the circuit. We can now also understand that in this simple electrical circuit of having only one load, the applied voltage of 120 volts is the same value as the voltage dropped across the LT1 load. The electrical circuit's total resistance is equal to the resistance value of the LT-1 load. Referring to the Ohm's law formulas, we can determine voltage applied to a circuit by multiplying the amps found anywhere in the circuit times the circuit's total resistance. In this example, 1 amp multiplied times 120 ohms equals 120 volts AC. The Ohm's law formula allows us to determine amperage by taking the applied voltage of 120 VAC and dividing this by the circuit's total resistance of 120 ohms. This gives us 1 amp that can be measured anywhere in the circuit, from terminal L1 to 1, from terminal 2 to N, etc. Finally, Ohm's law allows us to determine the circuit's total resistance by dividing the applied voltage by the circuit amperage. In this case, 120 volts AC is divided by 1 amp and gives us 120 ohms of circuit resistance. Simple electrical circuits are identified as having only one load. They could be applied with any voltage source and have loads represented different resistances, but they will always have only one load in their design. All electrical circuits can be measured using test instruments called multimeters. The multimeter can measure circuit voltage, resistance, and amperage. The multimeter, configured to read voltage, can read either the voltage being applied to a circuit or the voltage drop across the load. For the applied voltage, the meter is placed across the L1 and N terminals. For the voltage dropped across the load, the meter is placed across terminals 1 and 2. Notice that in both measurements, The voltage applied is the same as the voltage dropped across the load, 120 volts AC. Remember, we measure resistance of components that are disconnected from their power. We measure the resistance of the red lamp at 120 ohms. If we were to measure the total resistance of the circuit between L1 and N with the power removed, we will find also 120 ohms of total resistance. We can measure amperage of the circuit by taking our multimeter, configured for amperage, break the circuit, and then placing the meter in series between the L1 power source and a circuit load. We can also assume that the same amperage is found throughout the circuit, such as between terminals 2 and N. The last simple circuit law states that the value of 0 is equal to the applied voltage minus the voltage drop across the load. Just like our previous water circuit, we can see this applied voltage pressure being present at L1 and measured referencing termination N, we see 120 volts AC. Notice that if we measure the voltage between terminal 1 and N, we also see 120 volts. Now, measuring the voltage between terminal 2 and N, we see 0 volts. This proves that in the case of this simple electrical circuit, the value of 0 is equal to the voltage being applied to the circuit minus the voltage drop across the load. Recapping this presentation on simple electrical circuits, they only have one load, and in all simple circuits, the applied voltage equals the voltage drop across the load. The total resistance is equal to the resistance of that particular load. The amperage is the applied voltage divided by the total resistance, and 0 is equal to the applied voltage minus the voltage drop across the load.